Millions of worlds, billions of years, and almost none of them would let us live. 2.5 million light-years from Earth, a spiral of 1 trillion stars rotates in the cold darkness between galaxies. The Andromeda Galaxy. It is larger than our Milky Way. It is older. It contains twice as many stars. And somewhere within that ocean of light, there are planets. Rocky planets. Ocean planets. Worlds with skies that glow in colors we have no names for, and surfaces that would kill an unprotected human in seconds. But here is the question no one asks correctly. It is not whether humans could survive in Andromeda. It is what humans would become if they had started there. What forms would intelligence take on a world with 3 times Earth's gravity? What would eyes look like under a red sun that never sets? What kind of minds would evolve in an atmosphere of ammonia and methane? On a planet where a single day lasts longer than an Earth year? This is not speculation. This is applied physics, applied chemistry, applied evolution. And tonight, we are going to visit those worlds. You are aboard an unmanned probe. It was launched from a future Earth, carrying no passengers but a single directive: observe, record, and transmit. The journey took 2 million years at relativistic speeds. The probe has finally arrived at the outer edge of Andromeda. And now, one by one, we will descend into the atmospheres of alien worlds and ask the only question that matters. What would life look like here? The probe enters Andromeda from below the galactic plane, rising through the sparse outer halo, where ancient globular clusters drift like frozen cities in the void. Out here, the stars are old. Most are red dwarfs that have burned for 12 billion years. Remnants from a time before the galaxy had fully formed. Their light is dim, their warmth feeble. But they are patient. A red dwarf can burn for 1 trillion years. And that patience matters, because evolution takes time. The first target appears on the probe's sensors. A small rocky world, barely larger than Mars, orbiting a star so dim that the entire system would fit inside the orbit of Mercury. This is Kethrus, a world that exists in the habitable zone of an M4 class red dwarf. The star has no official name. It is simply one of 400 billion in the galaxy, but the planet it hosts may be one of the most common types of world in the universe. The probe begins its descent. Kethrus orbits at 0.031 astronomical units from its star. At this distance, a year lasts only 9 Earth days. The planet completes 1 full orbit before a week passes on Earth. But here's the consequence of that proximity. The star's gravity has locked the planet into synchronous rotation. One face always points toward the sun. One face always points away. There is no sunrise on Kethrus. There is no sunset. Half the world burns in eternal day, and half freezes in eternal night. The dayside surface temperature reaches 187 degrees Celsius. The rock glows faintly. Iron-rich minerals have oxidized into deep reds and blacks. Nothing can survive here in the open. The night side is different. It plunges to minus 143 degrees Celsius. Nitrogen freezes out of the atmosphere and falls as pale blue snow. Carbon dioxide forms glaciers that never melt. The ground is so cold that rock becomes brittle and shatters under its own thermal contraction. But between these two extremes runs a narrow ring, the Terminator Zone, a band of perpetual twilight where the temperatures might, just might, allow liquid water to exist. The probe adjusts its trajectory and descends toward this ribbon of dusk. The atmosphere is thin, only 0.4 Earth atmospheres of pressure. It is composed primarily of nitrogen and carbon dioxide, with traces of argon and water vapor. There is no ozone layer, no protective magnetic field. The star, despite its dimness, is a flare star. Every few days, it releases violent bursts of ultraviolet and X-ray radiation that would sterilize any exposed surface. So could anything live here? The answer is yes, but not where you would expect. The probe's ground-penetrating radar reveals something extraordinary. Beneath the basalt plains of the Terminator Zone, there are caves. Not small caves. Massive lava tubes, some stretching 40 kilometers in length and 200 meters in diameter. They formed billions of years ago, when the planet was still volcanically active. The lava drained away, leaving hollow tunnels behind. And those tunnels are shielded from radiation. Inside the caves, the temperature stabilizes. The rock provides insulation. Geothermal heat seeps up from below, and in the deepest chambers, the probe detects liquid water. Life on Kethris would begin here, not on the surface, not under the dim red sun, but in the darkness below. Now consider what kind of life would evolve in this environment. There is no sunlight underground. Photosynthesis is impossible. Instead, the base of the food chain would be chemosynthetic bacteria, organisms that derive energy from chemical reactions in the rock and water. On Earth, we find such bacteria around hydrothermal vents, thriving in total darkness. On Kethris, they would be the foundation of an entire ecosystem. Complex life would follow. Blind creatures, navigating by sound and vibration. Their bodies would be soft, because there is no need for UV-resistant skin. They would be pale, perhaps translucent, because pigmentation serves no purpose in the dark. Their metabolisms would be slow, because the energy available from chemosynthesis is limited. But here is the twist. The caves are not perfectly sealed. In certain places, cracks and fissures connect to the surface. And through those cracks, during the rare periods when the star is quiet, dim red light filters down. Not enough to see by, but enough to trigger something unexpected. Some organisms might evolve a primitive sensitivity to this light. Not eyes exactly, but photoreceptive patches. Cells that can detect the difference between light and dark. Over millions of years, this sensitivity could sharpen. Creatures might begin migrating toward the light during quiet periods, feeding on surface minerals or microbial mats that briefly flourish before the next flare. And that migration would drive the evolution of something remarkable. Creatures that live in two worlds. Underground most of the time, but occasionally venturing to the surface. Their bodies would need to handle both environments. Thick, radiation-resistant skin for surface excursions. Sensitive lateral line systems for underground navigation. Two modes of existence, separated by a few hundred meters of rock. Now imagine humans on Kethris. Not humans who arrived from Earth, but humans who evolved there from the beginning. What would they become after 50,000 generations? First, consider the gravity. Kethris has only 0.38 g, less than half of Earth's pull. Bones would not need to be as dense. Muscles would not need to be as strong. Over time, the Kithran human body would become taller, more slender. Limbs would elongate. The heart would shrink slightly, because it does not need to work as hard to pump blood upward. But the low gravity brings a problem. Without sufficient mechanical stress, bones lose calcium. They become brittle. On Earth, astronauts who spend months in microgravity suffer significant bone loss. On Kethris, evolution would need to find a solution. The answer might be behavioral. Kethran humans might instinctively engage in constant physical activity, jumping, climbing, grappling. Their culture might ritualize movement, building exercise into every aspect of daily life. Or the answer might be physiological. Their bones might develop a different mineral matrix, one that maintains density even under low stress. Next, consider the eyes. In the cave systems, light is scarce. The standard human eye, optimized for Earth's bright sunlight, would be nearly useless. Kethran humans would evolve enormous eyes with vastly expanded pupils. Their retinas would be packed with rod cells, the photoreceptors that detect dim light, and almost devoid of cones. They would see the world in shades of gray, exquisitely sensitive to the faintest glow. But when they venture to the surface during quiet periods, even the dim red light of the star would be painfully bright. They would need protective membranes, a nictitating membrane perhaps, like a shark or a camel, a translucent third eyelid that slides across the eye to filter excess light. Their skin would tell another story. Underground, there is no UV radiation, no need for melanin. Kethran humans would be pale, their skin translucent enough to show the blue shadows of veins beneath. But surface excursions demand protection. Perhaps they would evolve the ability to rapidly produce melanin on demand, their skin darkening within hours when exposed to radiation, and fading again when they return to the caves. Or perhaps they would never expose their skin at all. Clothing might become biologically integrated, not woven fabric, but secreted coverings, like the mucus coating of a fish. A second skin that absorbs radiation and can be shed and regrown. Their hearing would be extraordinary. In the caves, sound is everything. They would detect frequencies far beyond the human range, both lower and higher. They might communicate partly through infrasound, their voices carrying through rock over long distances. And they might use echolocation for fine navigation, clicking and listening to the returning echoes. Language would evolve differently on Kethras. In the echoing cave systems, words would blur and overlap. Clarity would demand either very short utterances or very precise timing. Kethran speech might be rapid and clipped, or it might rely heavily on pitch and rhythm, rather than complex consonant sounds that get muddied by echoes. Their architecture would be organic. They would not build above the rock, but within it. They would carve chambers and tunnels, expanding the natural cave systems over generations. Great underground cities might spread through the crust, connected by passages wide enough for crowds and narrow enough to defend. Light would come from bioluminescent organisms cultivated on the walls, living lamps that glow blue and green, descendants of the original chemosynthetic bacteria, modified through selective breeding. Food would be limited. Without sunlight, there are no plants, no grains, no fruits, no vegetables as we know them. The Kethran diet would consist of fungus, bacteria, and cave-adapted animals. Protein-rich, but monotonous. They might farm blind fish in underground lakes, raise insects in composting chambers, cultivate dozens of varieties of edible mold. Nutritional deficiencies would be a constant threat. Their medicine would focus heavily on supplements and careful dietary balance. And here is what changes everything. Fire would be precious. The atmosphere of Kethras has low oxygen content. Combustion is difficult. A flame lit on Kethras would be small and weak, prone to guttering out. The Kethran humans might never develop fire-based metallurgy the way we did. their technology would follow a different path. Perhaps electrochemical, perhaps biological. They might domesticate organisms that produce heat or light or corrosive secretions, using living tools rather than forged ones. This single constraint, the scarcity of fire, would reshape their entire civilization. No Bronze Age, no Iron Age. Instead, a biological age, a culture of careful cultivation, where every useful organism is bred and refined over centuries. They would be masters of directed evolution, shaping life to serve their needs because they could not shape metal. The probe lifts away from Kethris, its databanks full, but the journey has only begun. The red dwarf worlds are the most common in Andromeda. Trillions of them exist, and each one poses the same challenge. Too little light, too much radiation, tidal locking, flare activity. Life is possible on these worlds, but it is constrained, limited, pushed underground. What if we looked for something more like home? The probe accelerates toward the inner disk of Andromeda, where the stellar density increases. Here, in the spiral arms, younger stars burn brighter, and among them are K-type orange dwarfs, stars only slightly cooler than the Sun, stable for tens of billions of years, with habitable zones wide enough to host Earth-like worlds. The next target is a planet orbiting one such star. The probe designates it Varinthus. The star is K2V class, roughly 0.6 solar luminosities. It has burned steadily for 7.4 billion years and will continue for another 30 billion. In terms of stability, it is nearly ideal. No violent flares, no dramatic variability, just a patient orange glow, slightly cooler and redder than the Sun, but close enough that a human would find its light familiar. Varinthus orbits at 0.71 AU, where it receives approximately 1.19 times the solar radiation Earth receives. Slightly warmer, but not dangerously so. The planet is larger than Earth, 1.3 Earth masses, with a surface gravity of 1.12 g. The difference seems small, 12% stronger pull. But over millions of years, that difference adds up. The atmosphere is thick, 1.4 Earth atmospheres of pressure. Nitrogen and oxygen dominate, with 2.1% carbon dioxide, higher than Earth's, which drives a moderate greenhouse effect. Average surface temperature, 26 degrees Celsius. Warm, humid, tropical by Earth standards. The probe descends through clouds that shimmer with an orange tint, stained by the star's light. The sky is not blue here. Rayleigh scattering still occurs, but the star's output peaks at longer wavelengths. The sky of Varinthus is a soft amber during the day, deepening to bronze at the horizon. Below the clouds, the probe finds oceans, vast oceans, covering 81% of the surface. The land masses are smaller than Earth's continents, scattered across the globe like stepping stones. Mountain ranges rise sharply, where tectonic plates collide. Volcanic islands dot the seas, and everywhere, vegetation. Forests that reach towards the amber sky. But the plants are not green. Chlorophyll, the pigment that drives photosynthesis on Earth, evolved to capture the wavelengths of light most abundant in our sun's output. On Earth, that means absorbing red and blue light while reflecting green. But the K-type star of Varinthus produces comparatively more red and infrared light. Plants here would evolve different pigments, optimized for the available spectrum. The dominant color of Varinthian vegetation is dark red, almost maroon. Some species tend toward purple. Others are nearly black, absorbing every available photon. The forests look like they are burning. A permanent autumn. Leaves the color of dried blood. This visual shift has consequences. Herbivores that evolved to hide among these plants would need different camouflage. Predators would need different hunting adaptations. The entire visual language of the ecosystem would differ, and humans who evolved here would perceive the world differently. Consider the human eye again. On Earth, our color vision is trichromatic. We have 3 types of cone cells, sensitive to red, green, and blue light. This system evolved because distinguishing ripe fruit from unripe fruit and healthy vegetation from diseased vegetation provided survival advantages under the sun's spectrum. On Varanthus, the selective pressures would differ. The ambient light is redder. Distinguishing subtle shades of red and orange would matter more than distinguishing blue from green. Varanthian humans might be tetrachromatic, possessing 4 types of cone cells instead of 3, with additional sensitivity in the red and near-infrared range. They would see colors we cannot imagine. The maroon forests would shimmer with distinctions invisible to us. But here is an unexpected consequence. Blue light on Varanthus is relatively scarce. There would be less selective pressure to maintain sensitivity to it. Over many generations, Varanthian humans might lose some of their ability to see blue. The color would fade from their perception, becoming indistinct, blurring into gray. They would live in a world of warm tones, reds, oranges, yellows, and colors beyond red that have no name in human language. Their bodies would adapt to the higher gravity. 12% does not sound like much, but imagine carrying that extra weight every moment of every day. Varanthian humans would be shorter than Earth humans, stockier. Their bones would be denser, their muscles stronger pound for pound. Their hearts would work harder, their blood pressure slightly higher to push blood up against the increased pull. They might be more prone to varicose veins, to joint problems, to fatigue. But they would also be physically powerful. An average Varanthian, transported to Earth, would feel light and energetic. Their muscles, overbuilt for their home gravity, would make them remarkably strong by our standards. The higher atmospheric pressure would affect their lungs. With more air molecules per breath, they would extract oxygen more efficiently. Their chests might be smaller, their breathing slower, but they might also be more susceptible to oxygen toxicity if they ever visited a world with higher partial pressures. And nitrogen narcosis could occur at shallower depths during ocean dives. The pressure of Varanthus would be their baseline, and deviation in either direction would carry risks. The longer day matters too. Varanthus rotates once every 41 Earth hours. Each day stretches nearly twice as long as on Earth. This would alter circadian biology profoundly. Varanthian humans would sleep differently, perhaps in multiple shorter intervals rather than one long block, or perhaps in one very long sleep period, lasting 12 to 15 hours, followed by an equally long waking period. Their culture would reflect this rhythm. Activities might be organized around the long day in ways Earth cultures never developed. A single day might contain what we would consider multiple shifts. Morning work, a rest period during the brightest and hottest hours, afternoon work, evening activities, deep night, pre-dawn activities, and then sleep as the sun rises again. Time itself would feel different. A Varanthian would experience roughly half as many days in their lifespan as an Earth human, even if they lived the same number of hours. The 2 moons of Varanthus complicate the picture. The larger moon, roughly the size of Earth's Luna, orbits every 28 Earth days. The smaller moon, only 380 kilometers in diameter, orbits every 19 hours, racing across the sky in a blurred arc. Together, they create complex tidal patterns. The oceans of Varenthus do not simply rise and fall twice a day. They surge and retreat in overlapping rhythms, sometimes reinforcing each other, sometimes canceling out. Coastal ecosystems would adapt to this chaos. Creatures of the tidal zones would need to handle extreme variability. Sometimes the tide would barely move for days. Other times, it would swing through a range of 20 meters in a few hours. Varenthian shore life would be tough, flexible, and opportunistic. And any civilization that grew along those shores would learn to read the moons with obsessive precision. Tidal calendars would be essential. Predicting the tides would be one of the first mathematical achievements of Varenthian culture. Now consider something unexpected: the planet's axial tilt. Varenthus tilts at 41 degrees, almost double Earth's 23.5 degrees. This creates extreme seasons. Summers are brutally hot near the poles. Winters are long and dark. The equatorial regions remain more stable, but even they experience significant variation. Migration would be constant. No species could remain in one place year-round except in the most temperate latitudes. Birds, or their Varenthian equivalents, would traverse hemispheres twice a year. Large land animals would follow the seasons, moving hundreds or thousands of kilometers. Even plants might have evolved mobile seeds that ride the wind, or dormant stages that survive the extremes. Varenthian humans would be travelers by nature. Staying in one place would mean facing either scorching summer or frozen winter. Early Varenthian cultures would be nomadic, following the productive seasons, never settling permanently. Agriculture would develop late, if at all. Instead, sophisticated systems of seasonal exploitation might evolve, harvesting different regions at different times, storing surplus for the lean months. The psychological effect of this lifestyle deserves consideration. Humans evolved on a world where settling down and farming became the foundation of civilization. What would happen to a species where staying put meant death? Varenthian humans might have a deep, instinctual restlessness, a biological drive to move, to travel, to avoid stagnation. Their concept of home might be very different from ours, not a place, but a route, a circuit, a journey that repeats year after year, generation after generation. Attachment to land would carry different meaning. Ownership might apply to paths rather than plots. A family's wealth might be measured not in acres but in waypoints. The right to stop at certain oases, to harvest certain forests, to camp at certain favorable sites along the migration. War on Varenthus would look different too. Conquering territory would matter less than controlling choke points. Mountain passes, river crossings, coastal narrows where the migration routes funnel together. Fortifications might be temporary, erected each season and abandoned as the people move on. Or they might be permanent way station fortresses, garrisoned year-round by specialists who do not migrate, surviving the extreme seasons through stored supplies and careful engineering. The probe records all of this, its sensors mapping the planet's surface, its spectrometers analyzing the atmosphere, its cameras capturing the maroon forests and amber skies. Varenthus is more habitable than Kethrus. It is closer to Earth, but it is still not Earth. Humans who evolved here would be recognizably human, but subtly, pervasively different. Shorter, stronger, red-shifted in their vision, nomadic in their bones, sleeping strange hours under a double moonlight. The probe rises, leaving Varenthus behind. Not every world in Andromeda orbits a stable star. Some worlds drift alone in the darkness between stars, expelled from their birth systems by gravitational chaos. These are the rogue planets, sunless, cold, invisible, except by the faint heat they still radiate from their formation. There are likely billions of them in Andromeda, perhaps more than there are stars. The probe detects one by its thermal signature, a world slightly larger than Earth, adrift in the void approximately 12,000 light-years from the nearest star. No sun has warmed this world for 3 billion years. Its surface temperature hovers near -230 degrees Celsius. The atmosphere has long since frozen and fallen as snow. The oceans froze solid to a depth of several kilometers. This should be a dead world, and on the surface, it is. But the probe's instruments detect something unexpected. Heat is leaking from the interior. Not much, a few milliwatts per square meter, but enough to suggest that something is happening below. The planet's core has not fully cooled. Radioactive decay continues to generate warmth, and that warmth, trapped beneath kilometers of ice, has done something remarkable. There is liquid water beneath the frozen surface. An ocean, vast, dark, and eternal, sealed away from the cold universe above. The ice acts as insulation. The geothermal heat keeps the water liquid, and where there is liquid water and energy, there is the possibility of life. The probe cannot descend through kilometers of ice, but it can analyze. It can infer, and what it infers is haunting. Life in a subsurface ocean on a rogue planet would be utterly isolated. No light has ever reached this ocean. No seasons change. No days pass. The environment is stable in a way no surface environment can be. Stable for billions of years, unchanging, eternal. Evolution here would be slow. Selective pressures would be minimal. Why change when the world never changes? The creatures in this ocean might be ancient in form, simple, efficient. They would feed on whatever chemical energy the volcanic vents provide. Their bodies would be built for endurance rather than speed, for efficiency rather than adaptation. They might live for centuries, reproducing slowly, dying slowly, experiencing time in a way utterly alien to surface life. And here is the twist that changes everything about this world. The probe detects faint radio emissions from beneath the ice. Not natural emissions, structured, patterned. The kind of patterns that only emerge from information processing. Something in that ocean is intelligent, not necessarily technological in a way we would recognize, not building machines or launching signals into space, but processing information, communicating, thinking in the eternal dark beneath the ice. Something has awakened. How would intelligence evolve on a rogue planet? Without light, without seasons, without the pressures that drove evolution on Earth, what would push a species toward consciousness? Perhaps social complexity. If creatures in this ocean live in groups, if they cooperate to exploit the limited resources near volcanic vents, if they compete for mates and territory, then social intelligence would provide advantages. Remembering who helped you and who cheated you, predicting what others will do, communicating intention and warnings. These are the pressures that shaped human intelligence on Earth, and they could operate in any environment where complex social interactions occur. But the form of that intelligence would be alien, without eyes, without day and night, without seasons. The rogue world minds would not think in visual metaphors or temporal cycles. Their understanding of cause and effect might be different, operating on longer timescales. Their sense of self might be more fluid, less bounded. In an unchanging environment, the distinction between past and future might blur. Memory and anticipation might merge into something we cannot quite imagine. Communication would be tactile, acoustic, or chemical. They might speak through vibrations in the water, through touches and pressures, through chemical signals that linger for hours or days. Their languages might be slow by our standards, messages taking minutes to convey what we would say in seconds, but they would have eternity to talk. What is the hurry when nothing ever changes? If we imagine humans who evolved on this rogue world, not merely descended from Earth humans, but an intelligence that arose independently in the same form, they would be something beyond our comprehension. They would experience existence without light, without sky, without the rhythms that structure our consciousness. Their minds would operate differently. Their concept of reality would be different. We might share the label intelligent being, but we would share little else. The probe moves on, carrying data that will not reach any listener for millions of years. Deeper into Andromeda, the stellar density increases. The probe passes through one of the galaxy's major spiral arms, where young stars blaze hot and blue, where nebulae glow with the light of stellar nurseries, where supernovae have scattered heavy elements through space. This is a region of violence and creation, where stars are born and die in rapid succession. Here, the probe finds a world that should not exist. The planet orbits a blue supergiant, a star 25 times the mass of the Sun and 80,000 times as luminous. Such stars burn through their fuel in a cosmic eye blink, a few million years at most before they explode as supernovae. Any planet orbiting this star has been there for less than 5 million years. There has not been time for life to evolve from scratch, but life is present. The probe's spectrometers detect oxygen in the atmosphere in concentrations that suggest biological activity, biosignature gases, the chemical fingerprints of metabolism. Something is alive on this doomed world. The explanation requires stepping back. This planet did not form around the blue supergiant. It was captured. Once it orbited a calmer star, perhaps a K-type dwarf like Varanthus's sun. Life evolved there over billions of years. Then gravitational interactions, a close stellar passage, a perturbation from a massive neighbor, threw the planet loose. It wandered for millennia until it was captured by the blue supergiant's gravity. Now it orbits a star that will kill it. The intense radiation from the blue supergiant pours down on the planet's atmosphere. Ultraviolet light 1,000 times stronger than on Earth. X-rays streaming from the star's corona. The ozone layer, if one ever formed, has been stripped away. The surface is sterilized daily. Any exposed organism killed within hours. But life persists. Underground. In the oceans, beneath 100 meters of water that absorbs the worst radiation. In caves and crevices, where stone shields organic chemistry from the killing light. The life on this world is in crisis. It evolved for a gentler sun. Its biology is not adapted to these conditions. Species are dying. Ecosystems are collapsing. The planet is experiencing a mass extinction event. A slow-motion catastrophe that will climax when the supergiant explodes in a few million years. And yet some species are adapting. Evolution, when the pressure is extreme enough, can work fast. Generations are short. Mutations that would be lethal under normal circumstances become advantageous under radiation bombardment. The survivors are changing. Their DNA repair mechanisms are hyperactive. Their cells contain pigments that absorb and dissipate UV energy. Their bodies are developing new defenses in real time, an evolutionary sprint against extinction. Imagine humans caught in this scenario. A population somehow stranded on this captured world as it fell toward the blue supergiant. They would face a terrible choice: adapt or die. Those who survive would not do so through technology alone. Technology can shield individuals, but over millions of years, biological adaptation is unavoidable. The descendants of those first stranded humans would develop radiation resistance bred into their cells. Their skin would darken, not just with melanin, but with new pigments, perhaps based on different molecular structures entirely. Their eyes would develop multiple layers of filtering, protecting the delicate retinas from damage. Their immune systems would become hypersensitive to cancerous changes, destroying mutated cells before tumors could form. But the psychological effects might be even more profound. Living under a dying star, knowing that extinction is coming, would shape culture in ways we can barely imagine. Would they develop fatalism, a resigned acceptance of their fate? Would they develop urgent creativity, a desperate drive to accomplish everything possible before the end? Would they develop denial, myths, and religions that promise salvation or rebirth? Or would they develop something else entirely? A psychology adapted to impermanence, to living fully in the moment, because the moment is all that exists? A culture without long-term planning, without monuments, without legacies, because there is no future to plan for? The blue supergiant looms in their sky, 40 times the apparent size of Earth's sun, terrifying and beautiful, a harbinger of destruction that dominates every aspect of existence. They cannot ignore it. They cannot escape it. They can only live beneath it, adapted to its killing light, waiting for the end. The probe does not linger. This world is a tragedy in progress, but it demonstrates something important. Life is tenacious. Even on a world borrowed from another star, even under conditions that should be lethal, life finds ways to persist. It changes. It adapts. It survives until it cannot survive any longer. Deeper still, toward the core of Andromeda. The stellar density here is extraordinary. Where Earth's night sky shows a few thousand stars visible to the naked eye, the sky here blazes with millions. The Milky Way, seen from Earth, is a pale smear. Seen from the galactic core of Andromeda, it would be a river of light bright enough to read by. There is no true darkness at the core. Night does not exist. The combined light of packed stars provides perpetual illumination from every direction. The probe approaches a world embedded in this stellar furnace. The planet orbits an unremarkable G-type star, much like the Sun, but the star's location is anything but unremarkable. It lies within 100 light-years of Andromeda's central black hole, surrounded by millions of neighboring stars. The planet itself is Earth-like in mass and composition. It has oceans, continents, an oxygen-nitrogen atmosphere. From a distance, it could be Earth's twin, but the sky changes everything. There is no night on this world, ever. Even when the planet's surface rotates away from its local sun, the sky remains bright. Light pours down from every direction, the combined glow of millions of neighboring stars, washing out any darkness. The stars are so numerous and so bright that shadows are soft, diffuse, cast in multiple directions at once. The concept of darkness is alien to this world. Creatures evolving here would never experience true night. They would have no word for it, no concept of it. How would this shape life? Consider the role darkness plays on Earth. Night provides rest. It provides cover for nocturnal predators and prey. It drives circadian rhythms, the biological clocks that regulate metabolism and behavior. Without night, all of these dynamics change. Evolution on this world might never produce nocturnal species because there is no night to exploit. All creatures would be adapted to constant light. Sleep might still exist. The brain needs rest regardless of external conditions, but it would not be triggered by darkness. Perhaps it would be triggered by temperature changes or by internal cycles unconnected to the environment. Or perhaps creatures here would not sleep at all in the way we understand it, instead entering brief rest states throughout the day, never fully unconscious. Predation would be different. There would be no ambush, hunting under cover of darkness. All hunting would happen in the light. Camouflage would matter more than stealth. Speed and endurance would matter more than surprise. The ecology would favor the visible. Bright warning colors, elaborate displays, visual communication, and the psychological effect on intelligent beings would be profound. Humans who evolved here would never experience the mystery of night. The stars would not be distant points of wonder appearing in darkness. They would be an ever-present tapestry, overwhelming, inescapable. The sense of cosmic isolation that night gives us, the awareness of vast dark space stretching beyond our tiny world, would never develop. These humans might feel perpetually surrounded, embraced by the galaxy, part of a luminous community, rather than a single world alone in the void. But the core region carries dangers beyond eternal daylight. Stellar density brings stellar interactions. Stars pass close to each other more frequently here. Once every few million years, another star might pass close enough to the planet's orbit to destabilize it. The planet's climate might shift as it is nudged closer to or farther from its sun. Occasionally, a star might pass close enough to strip away the atmosphere or trigger massive tidal heating. Worse, the central black hole exerts its influence. It is not an immediate threat. 100 light-years is far enough for stable orbits, but its presence is felt. Stars spiral inward over billions of years, dragged by dynamical friction, eventually consumed. The neighborhood is transient. The planet's star might migrate inward in a few billion years, carrying the planet toward the black hole's accretion disk and certain destruction. Civilizations in this region would know this. Their astronomers would chart the slow inward spiral of the stars. They would know that their world is temporary, that eventually the black hole will claim them. This knowledge would shape their culture in ways we can only speculate about. Perhaps they would become obsessed with expansion, desperate to colonize other stars before their own is lost. Perhaps they would become philosophers of impermanence, developing psychologies that accept transience as fundamental. Perhaps they would deny the evidence, constructing mythologies that promise stability and permanence despite what their science tells them. The perpetual light and the looming doom would combine into a unique existential condition. Always visible, always watched, always reminded by the crowded sky that their world is just one among millions, and all of them are falling, slowly falling, toward the dark center. The probe continues outward now, leaving the dense core behind, moving through the transition zone where stellar density decreases. Here, the balance shifts. The stars thin out. Darkness becomes possible again. Worlds here might experience something like normal nights with millions of visible stars instead of billions. The probe selects its next target, a system in a globular cluster. Globular clusters are ancient structures, collections of hundreds of thousands of stars bound together by gravity, orbiting galaxies like moons. They formed early in the first billion years of the universe, and their stars are old, red giants, white dwarfs, dim red dwarfs. There are few young blue stars, almost no heavy elements. The planets here, if any exist, would be primitive in composition, iron poor, rocky perhaps, but lacking the complex chemistry that life on Earth depends on. The probe approaches Omega Andromeda 7, one of the massive globular clusters that orbit the galaxy's halo. Within the cluster, stellar distances average about 1 light year, 100 times closer than an Earth's solar neighborhood. The night sky from within the cluster would show roughly 100,000 visible stars, a celestial dome so crowded that individual stars might blur together in dense regions. But stars are only half the story. The probe searches for planets, and against all expectations, it finds one. The planet orbits a red dwarf near the cluster's outer edge, a region less dense than the core, but still remarkably crowded. The planet is small, about 0.7 Earth masses, with a thin atmosphere primarily of nitrogen and argon. Surface temperature, -43 degrees Celsius. Cold, but liquid water might exist in geothermally heated regions, or in deep saline aquifers that resist freezing. The remarkable thing about this planet is its composition. Metal-poor stars produce metal-poor planets, and this world is metal-poor to an extreme. Its crust contains less than 1/5 the iron concentration of Earth's crust, less than 1/10 the copper, zinc, and nickel. The heavy elements that life on Earth uses for enzymes, for oxygen transport, for cellular respiration, are scarce here. Life on this world, if it exists, would face a fundamental constraint: metal limitation. On Earth, the enzyme hemoglobin carries oxygen through our blood using iron atoms. The enzyme cytochrome C oxidase, essential for cellular respiration, uses copper and iron. Dozens of critical biological processes depend on metals. Without adequate metals, Earth life could not function. Life on this metal-poor world would need different solutions. Perhaps it would evolve alternative biochemistry, using more common elements to fill roles that metals fill on Earth. Perhaps it would be extremely efficient with whatever metals were available, recycling them obsessively, passing them from generation to generation. Perhaps it would exist at low metabolic intensity, slow and cold, avoiding the need for rapid oxygen transport. Imagine humans who evolved here. Their bodies would be different at the molecular level. Their blood might use a different oxygen carrier, perhaps vanadium-based, like some Earth sea squirts, or cobalt-based. Their metabolisms might be slower, their temperatures lower, their activity levels reduced. They would be physiologically sluggish by Earth standards, but adapted to their reality. Culturally, metals would be sacred. Iron would be worth more than gold is worth on Earth. Wars might be fought over metal-rich asteroids or rare ore deposits. Metallurgy would be a closely guarded secret, passed down through elite castes. Tools and weapons might be made of stone, ceramic, or bone, with metal reserved for the most critical applications, and their technology would develop along different paths. Without abundant metal, they would innovate in other directions. Ceramics, perhaps. advanced composites, biological materials, cultivated and processed organisms that provide strength and flexibility. Their machines might be grown rather than built, organisms bred for specific functions, metal-free and organic. The sky of this globular cluster world would provide its own wonder. 100,000 stars, glittering in a dome so bright that the concept of constellation would be impossible. Too many stars to group, too many patterns to distinguish. Navigation by starlight would be an overwhelming challenge. Maps of the sky would be useless. The reference points would blur together. These humans might navigate by other means entirely, by magnetic sense, by infrared heat detection, by echolocation or chemical trails. The probe collects its data and moves on, outside the globular cluster, into the sparse halo, and then back toward the spiral arms. The journey through Andromeda is a journey through extremes, from blazing cores to frozen rogues, from metal-poor wastelands to radiation-blasted capture planets. Each world demands different adaptations. Each world would produce different humans. The probe's next target represents another extreme, a circumbinary planet, a world that orbits 2 stars instead of 1. The system lies in the Andromeda's outer disk, a relatively quiet region where stellar encounters are rare and orbits remain stable for billions of years. The 2 stars are both K-type orange dwarfs, similar in mass and luminosity, orbiting each other every 41 Earth days. The planet orbits them both at a distance of 1.7 AU, taking 3.2 Earth years to complete one circuit. This is not a theoretical arrangement. We have discovered circumbinary planets in our own galaxy. They are less common than single-star planets, but they exist, and they present unique challenges for life. The first challenge is illumination variation. As the 2 stars orbit each other, the amount of light reaching the planet changes. When the stars are aligned with the planet, both on the same side of their mutual orbit, the planet receives maximum illumination, roughly 1.6 times what Earth receives from the Sun. When the stars are on opposite sides of their orbit, the illumination drops to about 0.9 times Earth's. Every 20 days, the planet cycles between warm and cool periods, not because of its own orbit or rotation, but because of the stars' dance. The second challenge is shadows. On a single-star world, objects cast 1 shadow. On a circumbinary world, objects cast 2. When the stars are close together in the sky, the shadows nearly overlap. When the stars are separated, the shadows split apart, pointing in different directions. The shadow of a tree might stretch east and west simultaneously, creating strange double penumbras. Life on this world would evolve under flickering conditions. The 20-day illumination cycle would become a fundamental biological rhythm, as important as the day-night cycle is on Earth. Plants might have 2 modes of photosynthesis, switching between them as the light intensity changes. Animals might have activity patterns tied to the stellar cycle, mating during bright phases, hibernating during dim phases. The double shadows would affect predator-prey dynamics. Camouflage would be more complex, needing to account for light coming from 2 directions. Predators might time their attacks for the confused moment when the 2 shadows cross. Prey might seek shelter during stellar opposition, when the double illumination eliminates hiding spots. For intelligent beings, the 2 suns would be fundamental to cosmology and myth. They might be perceived as a divine pair, creators and destroyers, locked in an eternal dance. The 20-day cycle might structure calendars, rituals, social rhythms. Philosophers might debate whether the two suns are one entity or two, whether unity or duality is the fundamental nature of reality. And navigation would involve two reference points, not one. The position of each sun would need to be tracked independently. Time might be measured differently, perhaps two separate systems, one for each sun, reconciled through complex calculation. The mathematics of circles and cycles would develop early, driven by the need to predict the celestial dance. Humans who evolved here might be more comfortable with complexity, with duality, with multiple causation. Their logic might be more naturally dialectical, seeing every phenomenon as the product of multiple interacting forces. The either-or thinking that sometimes dominates human discourse might be less common. Instead, a both-and perspective might prevail, an instinctive understanding that most questions have two answers that are both true, or perhaps not. Perhaps they would develop the opposite, a fierce desire for simplicity, for unity, for single explanations, as a reaction against the chaotic complexity of their sky. We cannot know without being there. The probe continues. There are worlds in Andromeda we have not yet visited. Worlds of ammonia, oceans, and methane rain. Worlds of crushing gravity, where evolution has produced flat, sprawling creatures that can barely lift themselves against the pull. Worlds of tidally heated moons, where the flexing of rock generates volcanoes and keeps oceans liquid even far from any star. Worlds of ancient white dwarfs, where planets that once orbited close have been engulfed and destroyed, and only distant survivors remain, slowly spiraling inward as their star cools. Let us visit one more extreme, a super-Earth in a system where the original star has already died. The star was once a yellow dwarf, not unlike the Sun. It burned for 8 billion years, exhausting its hydrogen, swelling into a red giant, casting off its outer layers, and finally collapsing into a white dwarf. The process took millions of years and devastated the inner system. Any planets within about 2 AU were consumed or vaporized, but the outer planets survived. And one of them, a super-Earth 5 times the mass of our world, survived in a slowly decaying orbit. The white dwarf glows with residual heat, a dense star about the size of Earth, but with half the mass of the Sun. It emits mostly ultraviolet light with little in the visible spectrum. From the surface of the surviving planet, the white dwarf would be a tiny, intense point of violet-white light, blindingly bright to look at directly, but providing very little warmth. The planet was once in the outer reaches of the original star's habitable zone, too cold for liquid water on the surface, but warm enough that subsurface oceans might exist under an icy crust. When the star died, even that feeble warmth vanished. The surface temperature plummeted. The atmosphere froze and fell. The oceans froze solid. For millions of years, the planet was dead. But white dwarfs cool slowly. And as this one cooled, its habitable zone contracted. The region where liquid water could exist on a planet's surface shrank toward the star. And by coincidence of orbital mechanics, the super-Earth is slowly spiraling inward. Gravitational radiation, interactions with the debris disk left by the star's death, drag it gradually closer. Now, 5 billion years after the star's death, the planet has entered the white dwarf's habitable zone. The ice is melting. The atmosphere is sublimating. Liquid water is appearing on the surface for the first time in eons. Life, if it survived beneath the ice during the frozen epochs, is emerging. This is a world being reborn. The probe descends through a thin atmosphere of nitrogen and carbon dioxide, freshly released from ice. Below, a patchwork of frozen and liquid regions spreads across the surface. Rivers run from melting glaciers into new seas. The geology is chaotic, adjusting to thermal changes after billions of years of stasis. And the life emerging from beneath the ice is strange. It evolved in the subsurface ocean during the long freeze. It never saw light. It never experienced the surface. Its adaptations are all suited to darkness, pressure, and cold. Now it is being exposed to conditions it never evolved for. Most species are dying. The UV radiation from the white dwarf, though feeble by stellar standards, is devastating to organisms with no UV protection. The temperature fluctuations are too rapid. The pressure changes are too extreme. The emergence is a mass extinction event, a flood of light and heat that destroys what darkness had preserved. But some species are adapting. Their evolutionary potential, dormant for eons, is being tested. Mutations that would have been neutral in the stable darkness are suddenly lethal or beneficial. Selection is intense. Evolution, which crept slowly in the unchanging depths, now races forward. In a few 100 million years, this world might host a complex surface biosphere. Creatures that evolved in darkness might give rise to descendants that thrive in the violet light. Intelligence might emerge if the conditions stabilize. Civilizations might arise on a world resurrected from death. But the window is closing. The planet continues spiraling inward. In another 2 billion years, it will be too close to the white dwarf, too hot for life. The resurrection will become another death. This world exists in a narrow epoch of possibility, a brief flowering between two extinctions. Humans who evolved here would know this. Their astronomers would calculate their world's trajectory, would know exactly how much time remains. 2 billion years seems long, but on cosmic scales, it is a deadline. Every achievement would carry a silent annotation before the end. Every monument would be marked temporary. Every dream would be bounded this far and no farther. Perhaps that knowledge would ennoble them. Perhaps it would crush them. Perhaps it would drive them outward, desperate to escape to other worlds before theirs becomes uninhabitable. Or perhaps it would turn them inward, focused on the present, savoring what they have while they have it. The probe rises from this haunted world, carrying records of life's tenacity and life's fragility. And the journey continues. Andromeda stretches across 500,000 light years. The probe has visited perhaps a dozen worlds in detail, sampled a few thousand more in passing. Even this represents an infinitesimal fraction of the galaxy's trillion stars. There are wonders the probe will never see, worlds we cannot imagine, forms of life and intelligence that would astonish even the most creative speculation. But certain patterns have emerged. Certain principles hold across environments. Life requires liquid, not necessarily water, but some medium for chemistry to occur. It requires energy, from stars, from geology, from chemical reactions. It requires stability, enough time for evolution to work. And beyond those basics, it requires opportunity, the right conditions at the right time, the chance for complexity to emerge from simplicity. Most worlds fail to provide these requirements. The universe is hostile to life. Most places are too hot, too cold, too irradiated, too chaotic, too dead. The exceptions are precious. And even among the exceptions, most produce only simple life. Microbes, films, colonies of single cells doing what single cells do. Complex life is rarer. It requires billions of years of stability. It requires the right evolutionary pressures, enough challenge to drive adaptation, not so much that everything dies. It requires luck, the right mutations at the right moments, and intelligent life is rarer still. It requires complex life to evolve in a direction that favors cognition. It requires the right environment to make intelligence useful. Social complexity, tool use, communication. It requires time for culture to develop, for knowledge to accumulate, for technology to emerge. When we ask whether humans could live in Andromeda, we are asking the wrong question. The right question is what humans would become if they arose in Andromeda. And the answer is everything we have seen and more. In the caves of tidally locked red dwarf worlds, human variants would grow pale and slender, blind to our colors, but sensitive to sounds we cannot hear. In the high-gravity tropics of K-type worlds, they would become short and dense, migrating eternally, speaking languages we would barely recognize. On rogue planets, they would evolve in eternal darkness, their minds shaped by silence and stability. Near dying blue supergiants, they would live fast and bright, knowing their world is temporary. In globular clusters, they would hoard metals like treasure, their biology constrained by scarcity. Around binary stars, they would learn to see double, to think in dualities, to navigate a sky that never stops moving. None of these beings would be us, but all of them would be human in some sense, descended from the same evolutionary pressures that produced intelligence on Earth, adapted to new pressures, diverging into new forms. Humanity is not a fixed template. It is a process, and that process would produce different outcomes in different environments. The probe carries this insight outward, broadcasting back toward a galaxy it will never see again. Somewhere, perhaps, intelligent beings are listening. Perhaps they will hear. Perhaps they will understand. Perhaps they will wonder about the worlds of the Milky Way, about what forms life has taken there, about what humans they might find if they sent their own probe to visit. The journey is far from over. The probe has power for another 10,000 years of operation. It will visit hundreds more worlds, thousands more systems. It will record data that no one may ever retrieve. But we have seen enough to draw a conclusion. Yes, humans could live in Andromeda. Not as we are, but as we might become. Not on every world, but on many. The galaxy is rich with possibilities, with niches where intelligence could find a foothold, with environments that would shape minds and bodies in ways we have only begun to imagine. The question was never whether life could exist. Life is stubborn. Life finds ways. The question is what life becomes. And the answer is, it depends on where you ask. The probe pushes deeper into Andromeda's spiral arms, where the stellar nurseries glow with the light of creation. Here, young stars emerge from collapsing gas clouds, surrounded by protoplanetary disks of dust and debris. These are the factories of worlds, the places where planets are being born right now, accumulating mass grain by grain, collision by collision. But the probe is not interested in worlds still forming. It seeks the strange, the extreme, the places where life would take paths unimaginable on Earth. And in a system approximately 47,000 light-years from Andromeda's center, it finds exactly that. The star is a young G-type, barely 2 billion years old, still settling into its main sequence stability. Around it, orbits a world that defies easy categorization. The planet is 2.1 times Earth's diameter, but 8.7 times its mass. This combination produces a surface gravity of 2.4 g, nearly 2.5 times what humans experience on Earth. The probe designates this world Graviton's Burden. Descending through the atmosphere, the probe encounters immediate differences. The air is thick, 2.8 atmospheres of pressure at sea level. The composition is familiar: nitrogen, oxygen, carbon dioxide, water vapor. But everything feels compressed, heavy, reluctant to move. Clouds hang low, dense with moisture. Rain falls in fat, heavy drops that strike the ground with audible force. The surface reveals the consequences of high gravity. There are no tall mountains. The rock cannot support them. Any peak that rises too high collapses under its own weight, spreading laterally, flattening. The highest elevations on this world reach perhaps 800 meters above sea level, comparable to Earth's modest hills. The landscape is a world of rolling plains, shallow valleys, and broad, sluggish rivers that meander across nearly flat terrain. The oceans are shallow. Without tall continents to create deep basins, the water spreads wide and thin. Average ocean depth, 340 meters. The deepest trenches barely reach 1 to 200 meters. Tidal patterns are muted, the water too heavy to slosh dramatically. Life here has evolved under relentless downward pressure. The plants are low, shrubs rather than trees, ground-hugging mats of photosynthetic tissue. Nothing stands tall because standing tall costs too much energy. Every centimeter of height requires structural support against 2.4 g of pull. The tallest vegetation on this world reaches perhaps 2 meters, and even that is exceptional, thick-trunked, broadly spread, more like a table than a tree. Animals are built for weight distribution. The dominant body plan is low-slung and wide, with multiple short legs spreading the load across a broad footprint. Creatures that on Earth might stand on 4 legs, here stand on 6 or 8. Spines are horizontal rather than vertical, running parallel to the ground. Necks are short or non-existent. Why lift a heavy head when you can keep it close to the body? Flight is rare. The energy required to generate lift against 2.4 g is enormous. Any flying creature must have huge wings relative to its body mass, and even then, flight is costly. The skies of this world are quiet. What flying creatures exist are small, insect scale, using membrane wings that beat furiously to stay aloft. Nothing larger than a sparrow takes to the air. But here is the unexpected adaptation. Some creatures have abandoned ground locomotion entirely and become aquatic. The oceans, despite being shallow, offer buoyancy that counteracts gravity. In the water, the crushing weight vanishes. Creatures that would be immobile on land swim freely through the shallow seas, their bodies supported by the dense, heavy water. And from these aquatic ancestors, intelligence may have emerged. The probe detects what appear to be artificial structures beneath the waves, geometric arrangements of stone and shell, cultivated beds of aquatic vegetation, pathways marked by deliberate placement of rocks. Something intelligent lives in these shallow oceans, something that never ventures onto land because land is a crushing prison. Imagine humans who evolved here, not on the land, but in the water. Their ancestors would have been aquatic from the beginning, developing intelligence in an environment where gravity's burden is lifted. Their bodies would be streamlined for swimming, with powerful tails and flexible fins. Their lungs, if they had lungs, would be adapted for breath holding or supplemented by gills. Their hands, the manipulators that allow tool use, would be webbed and strong, capable of fine motor control even in water. But they would know about land. They would see it from the shallows, that crushing realm where the water ends and the weight returns. They might venture onto beaches briefly, dragging themselves through the unbearable heaviness, but they could not stay. Their bodies are not built for it. Their muscles cannot support their own weight for long. Their bones would fracture under extended exposure. Land to these beings would be the hostile environment, the place of death. Stories might warn children away from the shore. Myths might describe monsters that walk on the dry ground, impossible creatures that somehow survive the crushing. And their civilization would be entirely aquatic. Cities built of coral and stone on the seafloor. Agriculture of kelp and shellfish. Metallurgy, if they developed it, would be conducted in underwater volcanic vents where heat is available. Their writing might be carved into shells or arranged in patterns of colored stones. Their music might be whale song, transmitted through water for hundreds of kilometers. They would never build rockets, never reach for the stars. The very concept of leaving the water, of traveling through the vacuum of space, would be almost unthinkable. Why would anyone leave the supportive embrace of the ocean for the crushing void beyond? Unless they developed technology that could carry water with them. Spacecraft filled with liquid, pressurized aquatic environments hurtling through space. Aquanauts rather than astronauts. Their vessels would be more like submarines than rockets, designed to contain ocean rather than air. The probe logs this possibility and rises from graviton's burden. Heavy world evolution produces aquatic intelligence, intelligence that may never reach the stars because the land itself is too hostile to allow the first steps. But not all heavy worlds are wet. The next target orbits a binary system approximately 12,000 light-years further into Andromeda. Both stars are K-type dwarfs, but they orbit each other at sufficient distance that their habitable zones do not overlap. The planet of interest orbits the larger star at 0.83 AU, receiving slightly more radiation than Earth. This world is also a super-Earth, 6.2 Earth masses, but its composition is different. It formed in a region of the protoplanetary disk, poor in water and rich in silicates and metals. The result is a dense dry world with a surface gravity of 1.9 GrE and almost no surface water. Desertum, the probe names it, a world of stone and dust. The atmosphere is thin, only 0.7 Earth atmospheres, and bone dry. Humidity hovers near zero. Clouds are non-existent. The sky is a deep violet brown, stained by suspended iron oxide particles, the same material that gives Mars its red color, but present in higher concentrations here. Rain has not fallen on this world for 3 billion years, and yet life exists. The probe's sensors detect organic signatures in the rocks themselves, not on the rocks, in them. Life here has retreated into the lithosphere, living within porous stone, extracting moisture from mineral hydrates, surviving in conditions that make Earth's driest deserts look like tropical rainforests. This is endolithic life, life inside rocks, taken to an extreme. The organisms are simple, bacteria-like microbes, single-celled and slow metabolizing. They spread through microscopic fissures in the stone, growing perhaps a millimeter per century. Their water comes from gypsum and other hydrated minerals, released through chemical processes and jealously conserved. Their energy comes from chemical reactions in the rock, oxidation and reduction cycles that proceed at glacial pace. But simplicity is not the same as impossibility. Given billions of years, even simple life can diversify. The probe finds evidence of multiple species, occupying different niches within the lithosphere. Some prefer certain rock types. Some tolerate higher temperatures, living deeper. Some have formed symbiotic relationships, exchanging nutrients through the microscopic channels of the stone. Could complex life evolve here? Could intelligence? The constraints are severe. Without surface water, without abundant energy, metabolism is limited. Complex organisms require more resources than simple ones. It is difficult to imagine how a large, active, intelligent creature could survive on desertum. But difficult is not impossible. Consider a different model of intelligence. Not a fast, hot-blooded creature like humans, but something slow and patient. An organism that lives for thousands of years, thinking thoughts that take decades to complete. Its body might be distributed through the rock, a network of cells connected by chemical signals, spread across hectares of stone. It would not move in any conventional sense. It would grow, slowly, extending itself through the lithosphere. Its intelligence would be incomprehensible to us. Time would mean something different. A conversation might take centuries. A decision might require millennia of deliberation. But it would still be intelligence, processing information, modeling the environment, making predictions, guiding behavior. And if such intelligence existed on desertum, would we even recognize it? The probe cannot answer this question. Its instruments detect chemistry, not cognition. It records the evidence of life and moves on, leaving desertum to its slow, stone-bound thoughts. The next target represents a different kind of extreme. Not gravity, not aridity, but chemistry. Approximately 23,000 light-years from Andromeda's center, in a region where the interstellar medium is enriched with heavy elements from past supernova explosions, orbits a world unlike any we have visited. The star is an F-type, hotter and more luminous than the Sun, and the planet sits at the outer edge of its habitable zone, 2.3 AU out, where the temperatures hover just above freezing. But the chemistry of this world is alien. The planet formed in a region where nitrogen compounds were exceptionally abundant. Its oceans are not water, but ammonia, liquid NH3, a substance that remains fluid at temperatures where water would freeze solid. The atmosphere is thick with nitrogen, methane, and trace ammonia vapor. The surface temperature averages -40 degrees Celsius. By Earth standards, this is a frozen hell. By ammonia standards, this is balmy. The probe descends through clouds of ammonia ice crystals, through a haze of organic aerosols, into a landscape of dark seas and pale shores. The ammonia oceans are deep, averaging 4,200 meters, and they are not empty. Life here uses ammonia as its solvent instead of water. This is not hypothetical. Astrobiologists have long speculated that ammonia-based life is possible. Ammonia dissolves many of the same compounds water does. It remains liquid over a wide temperature range. It can support the complex chemistry that life requires. But ammonia life would be fundamentally different. The chemical reactions that power Earth life depend on water's properties, its polarity, its hydrogen bonding, its ability to act as both acid and base. Ammonia has different properties. It is less polar. Its hydrogen bonds are weaker. It is a stronger base. An entire biochemistry would need to evolve around these differences. The probe detects complex organic molecules in the ammonia ocean, long-chain polymers, cyclic compounds, something analogous to proteins but built on different chemical foundations. There are structures that might be cells, bounded by membranes that function in ammonia rather than water. There are hints of metabolism, of energy being captured and stored and used. Life exists here. Ammonia life. Now imagine humans who evolved on this world. Not humans as we know them. Our biochemistry is fundamentally water-based and could never function in ammonia. But intelligent beings, shaped by the same evolutionary pressures that produced us, adapted to this alien chemistry. Their bodies would use ammonia-based biochemistry throughout. Their cells would be filled with ammonia instead of water. Their proteins, or whatever serve the same function, would be built differently, optimized for ammonia's chemical properties. They would be cold by our standards, their metabolisms running at temperatures that would freeze human tissue solid. They would perceive the universe differently. Their senses, evolved for different chemistry, would detect different signals. They might see in wavelengths we cannot, or hear frequencies beyond our range. They might have senses we lack entirely. Sensitivity to magnetic fields, to electrical currents, to chemical gradients that we cannot detect. Communication would be chemical as well as acoustic. In an ammonia ocean, dissolved compounds spread efficiently. These beings might release pheromone-like signals that convey complex information, emotional states, social status, individual identity. A conversation might be simultaneously verbal and chemical, words accompanied by scent signatures that add layers of meaning, and they would be utterly alien to us. This is the deeper truth of Andromeda's diversity. We have been imagining human variants, beings shaped by different gravities and different stars, but still recognizable as our evolutionary cousins. Ammonia life would not be our cousin. It would be something else entirely, arising from different chemistry, following different rules, thinking thoughts structured by different neurology. If we ever encountered such beings, communication might be nearly impossible. Not because of language barriers, but because of cognitive barriers. Their categories might not match ours. Their concepts might have no translation. Their experience of existence might be so different that we could share no common ground. And yet they would be intelligent. They would have their own science, their own art, their own questions about the universe. They would look up at the stars and wonder what other forms of life might exist. They might detect Earth's chemical signature and speculate about water-based organisms, just as we speculate about them. The probe rises from the ammonia world, carrying data that challenges the assumption at the heart of our question. We asked whether humans could live in Andromeda, but Andromeda may host beings so different from humans that the comparison loses meaning. The journey continues. Beyond the ammonia world, the probe encounters a system that illustrates another principle of planetary diversity: the importance of moons. The primary body in this system is a gas giant, roughly twice Jupiter's mass, orbiting an old K-type star at a distance of 5.3 AU. The giant is too far from the star and too massive to host life on its surface. Not that a gas giant has a surface in any conventional sense. Its clouds of hydrogen and helium swirl in bands and storms, beautiful but sterile. But the giant has moons, dozens of them, and one of those moons has caught the probe's attention. The moon is large, 0.9 Earth masses, and it orbits close enough to the giant that tidal forces knead its interior like dough. As the moon orbits, the giant's gravity stretches and compresses it, flexing the rock, generating heat through friction. This tidal heating keeps the moon's interior warm, even though the system receives little energy from the distant star. The surface is ice. Frozen water, dozens of kilometers thick, covering the entire globe. But beneath that ice, heated by the tidal flexing, lies a liquid ocean. And at the bottom of that ocean, where the mantle meets the water, volcanic vents spew heat and minerals into the darkness. This is Europa's cousin, 1,000 times larger. A world where the conditions for life exist not on the surface but sealed away beneath an icy shell. The probe cannot penetrate the ice directly, but it can analyze. The surface shows signs of recent geological activity. Ridges, fractures, regions where fresh ice has welled up from below. The ice is not static. It is churning, circulating, carrying material from the subsurface ocean to the surface and back again. And in that surface ice, the probe detects organic compounds, complex organics, amino acids, long-chain molecules consistent with biological processes. Something is alive in that ocean, and traces of it are being carried to the surface by the ice dynamics. Life under ice is not surprising. We suspect it may exist on Europa in our own solar system. But this moon is much larger, its ocean vastly more extensive. There is room here for complex ecosystems, for evolutionary diversification, for intelligence to emerge. What would intelligence be like in a world without sky? The beings who evolved in this ocean would never see stars. The ice above them would be their entire universe, a ceiling of frozen darkness pressing down. Below, the volcanic vents would provide the only light, dim bioluminescence and the glow of molten rock. Their world would be bounded, the ice above, the seafloor below, and the endless water between. They might not even understand that an outside exists. The concept of space, of vacuum, of other worlds, might be unthinkable. Their cosmology would be confined to their ocean. The ice would be the firmament, the seafloor, the foundation, the water, the whole of existence. And then, perhaps one day, they would drill upward. Out of curiosity, or the search for resources, or simple exploratory drive, they might begin to penetrate the ice. It would take generations, kilometers of frozen water, carved away by heat and effort. They would not know what lay beyond. They might expect more ice forever, an infinite frozen waste. Or they might hope for another ocean, a realm beyond the ice. What they would find is vacuum, cold, emptier than anything they could imagine. And above that vacuum, stars. The psychological impact would be shattering. Everything they believed about the nature of existence would be wrong. Their bounded, finite, comprehensible universe would suddenly be revealed as a tiny bubble in an infinite void. Species have gone extinct from less traumatic revelations. Or perhaps they would adapt. Perhaps they would develop the technology to venture out, to build vessels that could carry their water with them, submarines of a kind, pressurized and heated, voyaging through the cold nothing. They would be the strangest astronauts imaginable, aquatic beings evolved in eternal darkness, confronting the infinite light of the cosmos. The probe moves on, leaving the ice moon to its sealed ocean. The diversity of Andromeda extends beyond planets. Some of the most extreme environments exist not on worlds, but between them, in the accretion disks of compact objects, in the jets of active galactic nuclei, in the shells of expanding supernovae. These are environments too hostile for life, as we understand it, but they are not beyond imagination. The probe detects a neutron star approximately 8,000 to 700 light-years from its current position. Neutron stars are the collapsed cores of massive stars that have exploded as supernovae, objects containing more mass than the Sun, compressed into a sphere only 20 kilometers across. Their gravity is immense, millions of times Earth's. Their magnetic fields are trillions of times stronger. They spin rapidly, some completing hundreds of rotations per second. No life could survive on a neutron star's surface. The gravity would crush any material structure. The magnetic fields would tear apart any molecule. The radiation would sterilize anything within light years. But neutron stars sometimes have companions, and this one does. Orbiting the neutron star at a distance of 0.4 AU is a rocky planet, captured most likely during a close stellar encounter. The planet is 1.2 Earth masses and appears to have a thin atmosphere. It should not be habitable. The neutron star emits intense X-ray radiation that should strip away any atmosphere and sterilize any surface. But something unusual is happening here. The planet's orbit is edge-on to our line of sight, and the probe can watch it transit the neutron star. During transit, the planet's atmosphere absorbs some of the X-ray emission, and the absorption spectrum reveals something unexpected: heavy elements. Iron, nickel, chromium, in concentrations far higher than any natural atmosphere should contain. The atmosphere is artificial. Something is maintaining it. The probe cannot determine what. The radiation environment is too harsh for close approach. But the evidence is clear. Technological activity is occurring on a planet that should be lifeless. Someone, something, has found a way to survive in one of the most hostile environments in the galaxy. How would intelligence evolve in such a place? It almost certainly didn't. Whatever lives there now must have arrived from elsewhere, must have developed the technology to survive conditions that would destroy unprotected life. They are survivors, adapters, engineers who have bent even a neutron star's fury to their will. But what would living there do to them over time? The radiation would require extraordinary shielding. Life would be conducted underground or within heavily protected structures. Venturing outside would be impossible without advanced protective technology. The surface would be a hostile wasteland, visited only by machines. The psychological effects of such confinement would be profound. These beings would live in artificial environments their entire lives, never experiencing open sky or natural landscapes. Nature, for them, would be a historical concept, something their ancestors knew, preserved in records and stories, but never directly experienced. Would they remember what they lost? Would they mourn it? Or would they adapt so completely that the concept of natural environment would become meaningless, a quaint relic of a primitive past? The probe records its observations and continues. Not all of Andromeda's wonders involve extremity. Some involve subtlety, small differences that accumulate into large consequences over evolutionary time. The next target is a world so Earth-like that the differences seem trivial at first glance. The star is a G2V, almost identical to the Sun. The planet orbits at 1.004 AU, receiving nearly the same illumination Earth does. Its mass is 0.97 Earth masses. Its day is 25.3 hours. Its axial tilt is 21 degrees. It has one large moon, slightly smaller than Luna, orbiting every 32 days. From the probe's initial assessment, this world could be Earth's twin, but it isn't. The differences emerge on closer examination. The planet's atmosphere contains 24% oxygen compared to Earth's 21%. A small difference, but significant. Higher oxygen levels support faster metabolisms, larger body sizes, more intense fires. Earth's Carboniferous period, 300 million years ago, had oxygen levels around 35%, and insects grew to the size of eagles. This world has been at 24% oxygen for at least 1 billion years. The consequences are visible immediately. The vegetation is dense, lush, aggressive. Plants grow faster here, fueled by the abundant oxygen and the carbon dioxide their metabolism produces. Forests are thicker, taller, more tangled than Earth's. Decomposition happens faster too, driven by oxygen-hungry bacteria and fungi. Dead matter vanishes quickly, recycled back into the living system. Fire is more common. The higher oxygen makes combustion easier to start and harder to stop. Lightning strikes that would smolder on Earth ignite infernos here. The landscape is scarred with burn marks, forests in various stages of recovery from fire. Species have adapted. Thick bark, fire-resistant seeds, underground root systems that survive surface burns. And the animals are large. Oxygen limits body size in complex ways. On Earth, the largest land animals are constrained partly by how efficiently they can deliver oxygen to their tissues. Higher atmospheric oxygen relaxes this constraint. Animals can grow larger before oxygen limitation becomes a problem. The megafauna of this world are impressive. Herbivores the size of elephants are common. Some reach twice that mass. Predators scale accordingly. Pack hunters coordinating to bring down prey that a single individual could never challenge. The ecosystem is dominated by giants, with smaller creatures filling niches in between. Insects are larger too. On Earth, insect respiration through tracheal tubes limits body size. Higher oxygen extends that limit. This world has dragonfly equivalents with wingspans of 1 meter, beetle-like creatures the size of dogs, flying insects that pose genuine threats to small vertebrates. Now, imagine humans who evolved here. Their lungs would be slightly more efficient, adapted to the higher oxygen partial pressure. Their blood might carry hemoglobin variants, optimized for the altered conditions. Their baseline metabolism would run hotter, faster, consuming more energy and generating more heat. They would be more active than Earth humans. The abundant oxygen would support sustained exertion that would leave us gasping. Their endurance would be greater, their recovery faster. Athletes among them would achieve performances that would shatter every human record. But there would be costs. Higher oxygen means more oxidative stress, more free radicals damaging cells, accelerating aging. These humans might live shorter lives despite their vigor, burning bright and fast. Or they might evolve enhanced antioxidant systems, protecting their cells from the damage that free oxygen causes. Their fire use would be different too. Fire is more dangerous here, harder to control. Early humans on Earth used fire extensively, and it shaped their evolution and culture. Humans on this high oxygen world would learn to fear fire as much as use it. Their fire-starting techniques would emphasize control and containment. Their settlements would be fireproofed. Their myths would include fire as a dangerous necessary power, a gift that can destroy the giver. The larger fauna would pose challenges that Earth humans rarely faced. Predators the size of small buildings would require coordinated group defense with serious weaponry. Early technologies would focus on protection and deterrence rather than hunting. Walls, fire moats, noisemakers to drive off the giants. Hunting would come later, once the weapons were sufficient. The social implications are significant. Individual humans cannot stand against megafauna. Survival requires cooperation, coordination, group living. Early cultures on this world would be intensely social, with strong hierarchies and clear roles. Loners would die. Teams would live. The evolutionary pressure towards sociality would be even stronger than it was on Earth. And their megafauna would offer opportunities too. Once tamed, animals of that size could carry tremendous loads, pull massive weights, serve as living vehicles and construction equipment. Domestication would be a pivotal technology. The species that mastered it would dominate, their civilizations built, literally, on the backs of giants. The probe catalogs this Earth-like but not world, another entry in the encyclopedia of possibility. The journey extends further into the galactic disk, where young stars cluster along the spiral arms and ancient stars drift in the gaps between. The probe has been traveling for subjective months now, its processors cataloging an endless diversity of worlds. Each one presents the same fundamental question: what would life become here? And each one provides a different answer. In a system dominated by a bloated red giant star, the probe finds a world in the process of dying. The star was once sun-like, burning stably for 7 billion years. But its hydrogen fuel is exhausted now, and it has begun to swell, consuming the inner planets and baking the outer ones. The world the probe examines was once far outside the habitable zone. A frozen ice ball, perhaps, or a distant gas giant's moon. Now the expanding star has reached it, warming it, melting it, transforming it. Surface temperature, 67 degrees Celsius. Hot, but survivable. The ice that once covered this world has melted, releasing an ocean that now covers 94% of the surface. The atmosphere has thickened with water vapor, creating a muggy tropical greenhouse. Life that evolved in the frozen depths is now spreading across a suddenly hospitable world. This is a world experiencing a summer after billions of years of winter. The life here evolved under ice, in geothermally heated pockets, isolated and constrained. Now it has access to unlimited space, unlimited light, unlimited opportunity. Evolution is exploding. Species are diversifying at rates rarely seen in the fossil record. The ecological niches are empty. Every available lifestyle is open for the taking, and something intelligent is emerging. The probe detects tool use among a species of aquatic omnivores. Not complex tools, shaped stones, manipulated shells, nothing that would qualify as technology. But the foundation is there. These creatures are adapting to their sudden new world, exploiting its possibilities, developing the beginnings of culture. They have perhaps 100 million years before the red giant expands further and sterilizes the planet. That is not long on evolutionary timescales. Complex intelligence on Earth took longer than that to develop from simple beginnings, but it might be enough. The pressure is intense. The opportunities are vast. If they develop quickly enough, they might reach technological civilization before the star kills them. And if they do, they will know their world is dying. Their astronomers will calculate the star's expansion rate, will determine when the heat will become unbearable, will count down the generations remaining. Their entire civilization will exist under a deadline. Would that knowledge inspire them? Would it crush them? Would it drive them to the stars, desperate to escape before the end? Or would it turn them inward, focused on art and philosophy, and the pursuit of meaning in a finite existence? The probe cannot know. It can only record the beginning of their story and move on, leaving them to write the rest. Further into the disk, past stellar nurseries and supernova remnants, the probe finds something rarer, a world in a truly stable situation. The star is a K5b orange dwarf, old and steady, burning its fuel with miserly efficiency. It will last for 30 billion years, perhaps longer. The planet orbits at 0.42 AU, in the center of the habitable zone, where temperatures have remained stable for the star's entire 8 billion year history. The planet itself is tectonically active, recycling its surface, regulating its atmosphere through volcanic outgassing and weathering. This world has been habitable for longer than Earth has existed, and life has been evolving here that entire time. The probe descends through an atmosphere thick with the signs of biological activity. Oxygen at 19%, methane at trace levels, nitrous oxide produced by bacterial metabolisms. The surface reveals continents covered with vegetation, oceans teeming with life, an ecosystem as complex and interconnected as Earth's. Perhaps more so. 8 billion years of evolution. On Earth, complex multicellular life has existed for perhaps 600 million years. Intelligent life for less than 1 million. This world has had time for evolution to run experiments we cannot imagine, to develop solutions we have never conceived, to produce forms of life that would astonish us. The probe's cameras capture images of creatures unlike anything in Earth's fossil record. Organisms with body plans that evolved along different paths, exploiting possibilities that Earth life never discovered. Photosynthesis here uses different pigments, tuned to the orange dwarf spectrum, and the dominant color of vegetation is a deep blue-black. Animals display symmetries and structures that seem wrong to human eyes, but are clearly functional, clearly adaptive, clearly the products of intelligent design by natural selection. 6-legged is common. 8-legged is common. There are creatures that seem to have no clear front or back, that can move in any direction with equal ease, their nervous systems distributed rather than centralized. And intelligence? Perhaps. The probe detects structures that might be artificial, arrangements of stone and vegetation that seem deliberate, patterns that repeat too consistently to be natural. But there are no radio signals, no industrial emissions, no obvious technology. 8 billion years of evolution, and yet no starships, no cities, no transformation of the planetary environment beyond what biology does naturally. Why? One possibility: intelligence evolved and then went extinct, destroyed by asteroids or supervolcanoes, or its own internal conflicts, leaving only subtle traces that the probe detects as might be artificial. Another possibility: intelligence evolved and transcended technology, developing in directions that leave no physical footprint we would recognize. Perhaps they live in the ocean or underground or in some medium we cannot detect. Perhaps their technology is biological, indistinguishable from nature. Perhaps they are watching the probe right now, curious about this simple machine from a galaxy where intelligence is young. A third possibility: intelligence never evolved. 8 billion years, and the conditions for intelligence never quite came together. No social pressure, no environmental challenge, no evolutionary pathway that led to abstract thought. Life can be complex without being intelligent. Earth's dinosaurs ruled for 165 million years without developing technology. Perhaps this world's dominant life forms are just as successful and just as mindless. The probe cannot determine which possibility is true. It records its observations, notes the anomalies, and leaves the mystery unresolved. Some mysteries have no answers. Some questions can only be asked.